Okay, well, we can make a start. So hello, everyone. Thank you for joining this online seminar, which is part of the Good Vibrations seminar series. It's nice to see so many people online today. Today, it's my great pleasure to introduce Yaguang Li, who is a PhD student at the University of Sydney. Yaguang is an expert in all things red giants and scaling relations. And today, he's going to be talking to you about developing tools for probing solar-like oscillations. Over to you, Yaguang.
Right, thanks, Simon. Let me share my screen. Okay, so hopefully you can see that.
Yep, that looks good.
Yeah, awesome. Okay, thanks, Simon, for this nice introduction. Also, thanks for the steering committee of Good Vibrations seminar. I think this is a great initiative for PhD students. So I'm Yaguang, so I'm a PhD student here at University of Sydney. I'm in my third year right now, so I'm close to submission in February next year. And my thesis, my PhD research has been mainly focusing on developing the tools for probing solar-like oscillations. Just to remind you that the solar-like oscillations happen at the right part of the HI diagram. So the main targets I'm focusing on will be low mass main sequence stars, as well as low and intermediate mass red giants. So for the talk today, I will be mainly focusing on 3 questions. So in each part, I will focusing on answering one of these questions. So the first question is how to extract better stellar properties from stellar modeling. We all know that stellar modeling is a very good, very nice, magic way of getting stellar properties, but how can we do better than we've been doing? And the second question is related to testing the scaling relations. And the third question is that once we have all of these very nice astroseismic properties, what we can do about them. So the first question, how do we extract better stellar properties from stellar modeling? So in particular, I'm focusing on a very prominent issue in stellar modeling, and that is the surface effect. So what is the surface effect? So if you fit the stellar models for the sun and pick the best fitting model, you will notice that there is a discrepancy between the modeled frequencies and the observed frequencies. And this discrepancy will increase with the oscillation frequencies. So this is a known offset that our colleagues realized in the 90s. And the cause for this offset is that there is an improper modeling of the near surface layers, and this is what we call the surface effect. So if you do not correct this surface effect, the best fitting model is going to be a poor representation of the real star. And in general practice, the surface effect is corrected by some functional forms. And one of the most popular functions is something like this. So this small delta nu is the amount of surface correction. It is proportional to the frequency to the power of 3 and the frequency to the power of -1, and scaled by the mode inertia. So here the A3 and A-1 are just the 3 parameters that we need to determine. So how do we determine these 3 parameters in practice? So the values of A3 and A-1 are usually determined by fitting this delta nu as the actual discrepancy between a model and your observed frequencies. So as shown on the left, you can see this blue curve, which is this functional form, really nicely describe the model discrepancy between the model frequencies and the observed frequencies. And then you can essentially just correct the original frequency by adding this delta nu using the best fitted A3 and A-1 values. So then you get a set of corrected frequency, and then you can use these corrected frequencies to do whatever the modeling requires you to do, like doing inference, et cetera. But I think we're not completely free of problems. So let me show you what I mean. So here I'm showing some models along an evolutionary track. So each frame shows a particular model. The right panel is the HR diagram, and this shows, and on the left-hand side, on the top panel, I showed the observed frequency in these blue squares, and also showed the modeled frequencies in these open squares. And then the crosses show the corrected modeled frequencies. So these crosses are the frequencies that after we applied this correction. And the bottom panel shows the chi-square, the differences between the observed and modeled frequencies. So as you can see here, we probably can identify this one as the best fitting model according to chi-square, because that's the least chi-square. And you can notice, please pay attention to the amount of surface correction for this particular model. So if we take a look at the models just surrounding our best fitting model, like this one, or maybe this one, you'll notice the corrected frequency represented by the crosses do not change very much. But the original uncorrected frequencies have a lot of differences. So that creates a really big problem. If you ask me in particular for this model, do I believe the amount of surface correction is correct for this particular model? My answer would be no. And why is that? Because if you compare this model with respect to our best fitting model shown here, then these two models are not that so different in terms of their stellar properties. However, they have a really big difference in terms of the amount of surface correction, which is not that reasonable. So the problems with the current surface correction methodology is that the amount of surface correction can be unrealistically large or small, and it can only be determined with observational frequencies. So we can't just pick a model and ask ourselves, what do you think the amount of surface correction for this model is, which is not ideal. So our solution to these problems is that we can parameterize this amount of surface correction at nu max as a function of surface properties like gravity, temperature, and analyticity. So this dependency has been indicated by many 3D simulations as well as 1D non-adiabatic analysis. And of course, if you only have one star, you're not be able to constrain this this function, because one star only has one point in this gravity, temperature, and analytic space. So essentially, we want to fit all of the stars in a sample, doing an ensemble modeling across the HR diagram. And the result of this ensemble modeling to constrain the surface correction to let it vary smoothly across the HR diagram has a few benefits. So firstly, we can remove unrealistic surface correction values, and this is by construction, so there's not a bigger surprise there. And we can also reduce the scatter of model-derived properties, such as ages. So here am I showing the probability distributions of stellar ages for the RGB stars observed by Kepler. So left panel is one cluster and the right panel is another cluster. The top row is doing the surface correction, in the usual way, star by star surface correction. And the bottom row is we do the surface correction in an ensemble way, make the surface correction vary smoothly across the HR diagram. And immediately you can see that the individual, the age distributions for individual stars sort of clustered around the center values better. So there's not a lot of outliers compared to the method that we usually do. So that is a great benefit of applying this prescription for the surface correction. So some concluding thoughts on this. Correcting the surface effect in a uniform way helps improve inferred stellar properties. And I think the power, I think the ensemble modeling has been overlooked so far, and the power of ensemble modeling really lies in its ability to model correlated parameters. And surface correction is just one of the examples. We can also use this methodology to constrain other kind of parameters like mixing length, or maybe core overshooting subjoints, et cetera, and the list goes on. So that's the first part of today's talk. And the second part, we're going to move on to the scaling relations. And I'm going to describe some of the parts of the scaling relations, and I'll try my best to answer the question of how well do we know about them. So what are the scaling relations? So if we only focus on the solar-like oscillations, and the really nice thing about solar-like oscillations is that we now have observations of hundreds, thousands of them. And if we just pick some of them and look at the power spectrum, their oscillation patterns can sort of be represented by this universal pattern. So it kind of could be described by two parameters, just by the look of it. The first parameter is nu max, which is the nu max is the frequency where the sort of the maximum power appears. And another parameter is delta nu. So this delta nu is sort of like the regular is the frequency spacing where this regular pattern sort of repeats itself. And the scaling relation states that this delta nu, this quantity here is proportional to the mean density of a star, and you can convert it into mass and radius. The other scaling relation which states that the nu max is proportional to the acoustic cutoff frequency. So the acoustic cutoff frequency is basically the frequency above which the sound waves don't get reflected back, so you don't get to observe any modes above that frequency. And this, we know this acoustic cutoff frequency is proportional to the surface gravity and square root temperature. And then we just say, okay, we just say nu max is proportional to the surface gravity and the surface temperature. But the problem of this scaling relation, probably the most tenuous part of the scaling relation, is that it states that nu max is a fixed fraction of the acoustic cutoff frequency. So it's the first proportional sign is more troublesome. It's more of a guess. So the scaling relations, if you write that delta nu and nu max in and express it in mass and radius and temperature, and we can also rearrange these two relations to get mass and radius once we know the value of nu max, delta nu, and temperature. And the application of these two relations are very important in synergetic sciences. But we can also notice that in the current form of these scaling relations, we haven't really considered other second order effects of stars. We know stars show a broad spectrum of metallicity and rotation, or even magnetic field. All of these factors are not considered in the current form. So how big are those second order effects? So here am I showing all the observed Kepler red clump stars on a diagram. So let me explain this bit by bit. So here we only need to focus on the red points here. The red points are the red clump stars, the stars that are burning helium in the core. And the vertical axis is a combination of nu max and delta nu, and constructed in a way such that it removes the dependency on radius. So you can think it as a proxy of stellar mass. And the horizontal axis is nu max, which in this case is just a proxy of radius. Okay, so this is like a seismic mass and radius diagram. So immediately we can notice that all the red clump stars sort of form a very interesting pattern, and that is the hook that I'm talking about here. So this hook corresponds to the 0H helium burning phase. So a star, once it starts to burning helium, it will first sit on this black dashed line and then gradually evolves to the left on this diagram. And so once we look at this interesting pattern here, then we can ask ourselves, what if the delta nu or the nu max scaling relation doesn't relate to the stellar properties that good? Okay, so what if there are some intrinsic scatter inside delta nu and nu max scaling relation? So here's the result. So if we scatter both delta nu and nu max, just add some scatter to the delta nu and nu max, scatter both quantity by 10%, what we're getting is like a, I don't know what to call it, but it's just a very smearing feature here. You can't basically see any kind of feature. And the 0H helium burning phase will not be as sharp as we see earlier. So this indicates that we can actually use the sharpness of this feature to constrain the intrinsic scatter of the scaling relations. Because if the scaling relations doesn't work really well, or do not work really well, then we're not be able to see these features in such a sharp form. So what we do is we take out the observational sample observed by Kepler, and we also generate some synthetic sample from simulations. And then we can sort of add artificial scatter to the synthetic sample and compare the sharpness of the synthetic sample with respect to our observed sharpness. The result of that is that we can constrain the sharpness, constrain the intrinsic scatter of the scaling relations to a few percent. So for the mass is like 1.7% and radius is 0.4%. So this precision is way, way smaller than typical uncertainties that we expect from measuring delta nu and nu max as such. So the conclusion of this is probably the intrinsic scatter of the scaling relations probably do not really have anything to worry about. I want to move to a slightly different aspect. So other than the intrinsic scatter in these scaling relations, we can also sort of study the deviation of the systematic offset of these scaling relations. So now you can see I have changed the formatting of delta nu and nu gamma scaling relation by plugging into a correction factor, FD nu and F nu max. So under normal circumstances, these correction factors should be around 1, and a departure from 1 indicates a departure of the scaling relations themselves. So if I take into account of these correction factors and look at the new scaling relations, these correction factors will appear in the denominator of these fractions. So how do we constrain or know these correction factors, the values of these correction factors? We can utilize the, for example, we can utilize the independent measurements of masses and radii and compare these seismic masses and radii, and that will gives you a solution of FD nu or F nu max. And examples of this are including binaries or astrometric radii, cell clusters, interferometric radii, etc., etc. But we can also try to understand and learn these correction factors from stellar models. And in particular, for the FD nu correction factor, there is a whole business going on trying to just calculate this correction factor from stellar models. And the way to do that is that we can solve the oscillation frequencies given the stellar model, and then use these frequencies, we can calculate the delta nu. And then this delta nu can be compared with the mean density of this model, which yield the FD nu correction factor. And the good thing about this method is that now you can map this FD nu as a function of stellar mass, age, and metallicity. Or you can just map it as any combination of observables you want. One bit that I haven't really mentioned before is that in the work of surface correction, now we can correct the oscillation frequencies with the surface effect. So for previous works, people don't really have the ability to just pick a model and ask how much surface correction I need in order to bring these frequencies, to reality. But now we can consider this surface effect on the theoretical F delta nu, because we can correct these theoretical oscillation frequencies. And so on the left-hand side, I showed the fractional change of this correction factor due to this newly considered surface correction. And as you can see here, basically on the RGB, where the effect is more prominent, is roughly around 2%. And 2% may not sound like a big deal for F delta nu, but if you look at the equation, you realize that the mass is dependent on FD nu to the factor of 4, and radius is dependent on FD nu to the power 2. Then that indicates mass needs to be changed like 8%. Radius needs to be changed like 4%. That's a big deal, I would say. So we can use these newly calculated F delta nu correction factors to derive the astroseismic radii using the scaling relations. And we can compare them against the Gaia radii. So here on the left-hand side, I show the fractional differences of the two radii. And so for the black circles and the blue triangles, these are the F delta nu correction factors that derived without considering the surface correction. And although they are derived using different sets of stellar models, you can sort of see they agree pretty good with each other. So in this case, I would like to say that model uncertainties are probably not a major issue when we are making this correction. And if we consider the surface correction, we can, which is represented by all of these red squares, you can see all of the points sort of moving downwards for like 4% or something. So, but still, these new FD nu values are still within the error budget, which is indicated by this gray band, because there are some systematic errors involved when we are calculating our Gaia radii. And one interesting bit is that around radius around 15 solar mass, there is an excursion of points. And we believe that this excursion of points is possibly due to the AGB bump for some metallicities happening here. So there is an overdensity of AGB stars. So there is a contamination of AGB stars, which makes the FD nu correction basically erroneous. The effect of this clearly deserves some further investigations. And we can also compare using our newly derived FD nu correction factors with eclipsing binary properties. So here I'm comparing the astroseismic masses with dynamical masses and astroseismic radii with dynamical radii. So the blue triangles are the values that without surface correction considered, and the red points, red squares are the points that with surface correction considered. So you can see using this new correction, we can get a much better agreement. Okay, so what about at the F nu max correction factor? So it turns out that although we can't reliably predict the values of nu max from a stellar model, we can still answer this question to some extent. So there are numerous studies suggesting that the nu max could be related to the metallicity of a star. I mean, it's not a crazy assumption because nu max relates to the excitation process of a star, which happens at the near surface region. So there are some theoretical work suggesting there should be metallicity dependency. And from the observations of extremely metal poor stars, we also noticed that there is a mass inflation based on the mass calculated from seismic scaling relations. And although the knowledge of this issue has been kind of evolved right now, because I think the current understanding is that the temperature for the metal poor stars are kind of off by a few percent. But still, we would like to know whether nu max is related to the metallicity. So we can calculate this F nu max correction factor by dividing the nu max, the observed nu max, which is the true nu max value, by the nu max that we derived from the stellar modeling and calculate based on the scaling relations. And the denominator, this nu max, can be constrained by all kinds of observational observables like luminosity, frequencies, etc., etc. So here I'm showing the F nu max versus metallicity constrained by luminosity and radial modes only. So now you can see a really nice dependency of F nu max versus metallicity. If you add on the quadruple modes, then the scatter, then the relation sort of tightens up a little bit. However, we noticed that the biggest uncertainty from this exercise actually comes from the poorly constrained mixing length parameter. So if we plot the distribution, you just pick one star and plot the distribution of alpha mixing length and the F nu max, we can clearly see a very strong correlation here. So if I change the mixing length parameter a little bit, then we can shift this F nu max value by a large amount. So how do we solve this problem? So we don't know the exact values of these mixing length parameters previously. So if we can just use the calibrated mixing length parameters from eclipsing binaries, for example, then we can pretty much see that this metallicity trend vanishes. To conclude, I think we can safely say that no metallicity dependency of F nu max correction factor is found within the current observational precision. So some concluding thoughts. We need to account for the surface effect of the FD correction factor and the F nu max around 1, and the potential dependency on metallicity really depends on how well we know the mixing length parameters. There are some uncertainties in stellar models, just like the mixing length. These can be mitigated by ensemble modeling and some independent calibrations, such as the properties from eclipsing binaries. And when you're really using these scaling relations, just keep in mind that there are various types of uncertainties will also factor into your calculation. And there are some really good review about that. Okay, so the final part of my talk is going to be trying to answer the question, how can we do, what can we do with these really good, really nice astroseismic properties? And I'm sure everyone has their own answer, like you can do it, use it to study your favorite planets or do galactic archaeology. So I'm focusing on one particular example, and this example is our discovery of post-mass transfer rate clump stars. And this discovery is purely based on the fact that we have better properties than before. So if you remember this plot, which is the seismic mass and radius diagram, and this is the zero-age helium burning phase. And I said earlier that stars will evolve leftwards. So here I plotted some evolutionary tracks with various masses. And as you can see, generally, overall, the theoretical evolutionary tracks describes the observational sample pretty well. So, but there are some outliers that lies on the right-hand side of the zero-age helium burning phase. And we have checked those stars, and they are really genuine. They're genuine detections. So after cleaning the sample a bit, we notice there are a few stars that lies on the right side of the zero-age helium burning phase. And this can't really be readily explained with single stellar evolution. And we call them underluminous stars in this case. So if we're back looking at this diagram, we also notice that the bottom part of this hook sort of got smeared out. It kind of blurry. So we also checked this this bottom end, and we realized that these detections are also real. And what's more interesting is that we used the scaling relations to calculate the stellar their masses. Then we got a remarkably low mass. And a star with this kind of low mass can't really exist within the age of the universe. So how do they form? How do they get such a low mass? So in summary, we discovered two types of stars that can't be readily explained by single stellar evolution. So one type of star is called underluminous stars, which lies on the right-hand side of the zero-age helium burning phase. And another type is called very low mass stars, which are located on the bottom part of this hook-like structure. So so how do we explain their position on this seismic diagram? So here I'm plotting some theoretical evolutionary tracks here. So all the all the black solid line here are evolutionary tracks from a single stellar evolution. Here I'm showing a bunch of masses from 0.6 all the way up to 2.0. And I'm also showing if I evolve a star with an initial mass of 1.5 solar mass, which is indicated by this light blue lines, and then the model just got stripped out of some of the masses from the surface on the RGB tip, and then it and then it will and then it will get the final mass indicated by these numbers 0.6, 0.8, etc. So basically, in this case, you can see these blue tracks are overlaid exactly on these black tracks, which indicates if a star that starts with a 1.5 solar mass and then end up with these final masses, then their stellar properties are just going to look exactly like the regular stars. There's no way to distinguish between them. However, if I start a stellar model with a slightly higher mass, like 2.2 solar mass, then if I lose various amount of mass on the RGB tip, then I got a series of evolutionary tracks on the right-hand side of the 0H helium burning phase. And the reason for that is that for a 2.2 solar mass star, it will have a smaller core inside the star. So it will basically have a less energy source to generate luminosity to support the star. And that's why we're seeing these stars have a smaller radius, smaller luminosity. And the last bit, I want to mention an example, also relates to the application of astroseismic properties that we can really make use of the galactic age velocity dispersion relation to do some really cool stuff. So what is the age velocity dispersion relation? So this relation states that when a star is born in a galaxy, then as time goes by, the velocity of the star will be sort of dynamically heated up. So the velocity dispersion will get larger and larger. So as indicated recently, so here am showing the velocity dispersion as a function of various parameters. But in the second column showing here, I'm showing its relation with respect to age. And we can see there is a clear dependency between the velocity dispersion as well as the stellar age. And this has been validated across different surveys, of course, as you can see indicated by the different color lines here. So what this means for us. So I think what this means is that this effectively means that we have now stellar isochrones for field stars. So the velocity dispersion for a group of stars will increase with the mean age for this group of stars. There are already very interesting works utilizing this velocity dispersion to indicate that this velocity dispersion really depends on age. So this example showing that the famous gyrochronology diagram showing period versus temperature for main sequence stars. So a star will basically evolve upwards in this diagram, and it is color-coded by the velocity dispersion in each beam that's showing in this diagram. And you can see as the star gets older, its velocity dispersion gets larger. So what does this mean to us? Like, how can we make really good use of astroseismic properties? So one example is that we can actually use this age velocity dispersion relation to probe the mass loss, the integrated mass loss on the RGB. So on the left-hand side, I'm showing Kepler astroseismic red giant sample. So on the top panel is all the RGB stars, and the bottom panel is all the red clump stars. And I'm showing all the stars on the spectroscopic metallicity versus astroseismic mass plane. So a star will first become an RGB, then a red clump. And I have divided this parameter space into all these sorts of bins and calculate the velocity dispersion inside each bin, which is indicated by the color here. So as you can see here, by comparing the difference between the two panels, you can sort of see that this color gradient sort of move leftwards from top to bottom. And the same color indicates basically the same age. So what this means is basically stars will lose about 0.1 solar mass at the tip of RGB. And this value it has been confirmed using observations of open clusters, but now essentially we can do a lot more with field stars because now we can explore this amount of mass loss as a function of metallicity and mass, which is something that we can't really do before with only a few open clusters. So astro seismology, once we have the great stellar properties, can really probe other stellar physical processes, and this age velocity dispersion relation can be really served as a great age ladder in order to really make good use of our great astroseismic properties. Okay, so that's basically my talk, and here's a summary page. So ensemble modeling can constrain uncertain stellar physics, and I hope more and more people will use ensemble modeling to constrain these uncertain stellar physics. And the scaling relations probably have nothing serious to worry about unless you push that to the extremes, which definitely needs more tests in the future. And astroseismology can really empower the calibrations of stellar models and offer precision probes for many physical processes. And finally, the better stellar properties benefit everyone. Everyone loves better stellar properties, and better stellar properties will reveal new patterns, and in often cases, that means new physics. Okay, thank you.
Thank you, Yaguang. That was a really comprehensive talk, touching on so many different things. Actually, I'm really impressed. Thank you. Well, I have many questions, but first we'll open it up to the floor. Does anyone have any questions for Yaguang? Connie has a question. Go ahead, Connie.
Hi, everyone. Thanks for this comprehensive seminar. I have a question on your first part. So maybe you said it, but then I missed it. There's football in the background here, so maybe that's the reason. But so once you have done this better correction for the clusters that you showed, the two clusters, right, the Kepler ones? Yeah. So at that stage, for each pulsator in the cluster, you know how wrong you were when you did not treat it as an ensemble, right? In terms of correction. Did you look at these differences and try to connect them with the physical properties of each of the stars? Because you could learn something from that. You see, you see what I mean?
Yeah, I actually haven't done that, but I think that's a great suggestion.
Yes, I would like to see that actually, and in a statistically solid way, to see if you can relate that to the properties of those stars.
Yeah. And I guess one of the comments is that we know that perhaps there is not a big of a change in terms of the center value, but in terms of the scatter, we can indeed see there is a reduction of scatter. But indeed, we can look at what are, for example, the stars that with a large scatter, what are these models are doing wrong, right?
Yeah, that would be interesting. Okay, thanks for that.
A related point there, Yaguang, is to what extent are the top panels influenced by just not having a good age prior? I mean, having ages greater than 15 gigayears just doesn't make sense, right? So, to what extent could just a better age prior also help here?
So I'm not exactly sure. Obviously, that requires some recalculation of the grid. But we also know that so just by looking at these posterior distributions, we can sort of say that if you just cut out the models above 15 gigayear, probably you're going to be just fine, I would say. There's not a lot of stars that has some probabilities above 15 gigayear. But the other issue is that although we know a star can't be older than 15 gigayear, however, for the stellar physics, if you do not account for some physical process in your models like diffusion, etc., then you're not going to get the right age. So I'm not sure how that will play a role in terms of getting the absolute age in this exercise. So I guess that's really requires some further comparisons of different models with different kind of physical settings. Yeah,
okay, thank you. I apologize if people can hear construction noise in the background. Unfortunately, I can't do anything about that. Do we have any more questions for Yaguang? I don't see any hands raised at the moment. If you could go to the slide on your underluminous stars, which stand out very nicely in that diagram. Yeah, so the implication here is that the underluminous stars, have they necessarily lost mass to a companion, or are they just shedding mass on the red giant branch through other mass loss processes? What do you think is happening there?
That's a good question. So I think what's happening here is that these stars have experienced excessive mass loss, which can't really be explained by single cell evolution. So, so our interpretation is that these masses are lost to a companion. However, if you really want to confirm this theory, probably you can look at radial velocities in order to just find a companion. And if you can't really find any radial velocity anomalies, maybe that that excessive mass loss happened during some very violent merger process. That's another hypothesis. And in that case, you can essentially look out for chemical anomalies, because these binary process tends to screw up the chemical signatures. So yeah, I guess the question in a simple answer is that, yeah, I do believe these are from binary evolution, not single cell evolution.
And so have you looked for radial velocity variations or chemical anomalies or anything like this?
Yeah, so for the radial velocity, we did. And I think the initial conclusion is that there are only a few, like 1 or 2 stars in our sample that have radial velocity variations, which is really weird. So that really put a puzzle for us, that how do we explain the evolution of these stars? And with respect to the chemical signatures, we did look at, for example, lithium abundance of these stars, as well as the carbon-nitrogen ratio of these stars. And a large fraction of these stars do have chemical anomalies. So yeah, to be honest, we have no clue of how these stars form at the current stage. So if you have any better ideas, theories to explain their formation, I'd really love to hear about that.
Okay, I'll let you know if I think of something. Tim Bedding has a question. Go, Tim.
Thanks, Alvaro. That was great. So the other weird thing that can happen to stars is mergers, of course. So 2 smaller stars can make a slightly bigger one. Yeah. Where does that fit into this scenario? Could some of these weird stars be mergers rather than mass loss?
Yeah, so I guess one thing about merger is that the merger process doesn't have to be mass conservative. Because during the mass process, at some phase, I would expect I would expect the common envelope evolution, where basically the 2 stars are all surrounded by a common envelope, and during that phase, the system could potentially just shed a lot of mass during this process. So if you have two stars, then the merger products, the final mass, is possible that the final mass doesn't add up. The two stars' individual mass doesn't add up to the final mass of the merger product. That's what I'm saying. So yeah, so in that sense, I completely think it's possible that the merger is a potential evolutionary path for these objects, in the sense that the progenitors doesn't necessarily have to be a smaller mass stars compared to these stars we found here. But regarding the detailed evolution paths of these systems is still kind of a mystery, I guess.
Yaguang, could you go to the slide with the age velocity dispersion relations?
Yes.
You're one, 2 slides down from here.
Okay.
Yeah, this one. So you're finding an overall shift between the red clump and the red giant branch.
Yes.
And I guess the maximum age difference or fractional age difference between the two is about 10%, right? Like stars spend about 10% of their main sequence lives, like that equivalent amount of time, then burning helium in the core in the red clump, right? So is the shift that you see compatible with just a 10% difference in age?
I guess not really, because the stars that are locating on the RGB. So the RGB is a quite fast evolving phase. So all of the stars shown here are red giants already. So the red giant phase is a super fast evolving phase. So the age difference between red giant branch stars and the red clump stars can't be explaining the huge difference in terms of mass that's showing here, which can only be related to mass loss. And I guess this point has been really nicely pointed out within a few open clusters that Kepler observed. So yeah, I guess that's the question.
Well, so you just said about stars that are in open clusters, but I thought that this age velocity dispersion relation was for field stars.
Yeah, that's right. What I'm saying is that in open clusters, when we're comparing the average mass of RGB stars and the average mass of red clump stars, we do indeed find that there is like a 0.1 solar mass difference. So that's what we found. Using open clusters, and now we're seeing basically exactly the same thing with the field stars, but compared to the open clusters, now we have more metallicities and more masses to explore. So I think that's the advantage of this exercise.
Gotcha. Yeah. Okay. Cool. All right. One last call for any questions for Yaguang. Don't be shy. Savita has a question.
Yes, hi. Thanks for a very interesting talk. It's more of a curiosity about the surface corrections, because I know there are people like Ragnar Trumpedak who's doing like 3D simulations to look at the surface effects. So I was wondering if you compared your results with what he was finding, or if you're planning.
So I have already did that, but the problem of the amount of surface correction is that I think, well, there are several complicating factors involved. First, the 3D models so far, as far as I know, only looks at the sort of the structural effect. If you replace the 3D model with the surface layer of a 1D model with 3D models, you're only accounting for the equilibrium structural difference. You're not really counting the non-adiabatic, the so-called modal effect, which is the interaction between pulsation and convection. So it's already kind of hard to directly compare the amount of surface correction from 3D inferred from 3D models with respect to the values shown here. And on the other hand, we also know that even only for 1D stellar models, if you use different kinds of surface boundary conditions, then you will get very different amount of these surface correction values. So that's another complicating issue here. So I guess it is not that easy to directly compare the absolute value of these surface correction values. However, we did compare the sort of the overall trend of the surface correction with respect to these three parameters like gravity, temperature, and velocities. And the overall trend do agree with each other. So I can say they agree with each other qualitatively, but not necessarily quantitatively. Yeah.
Okay, thanks.
Alrighty, I think we'll leave it there for today. If you would like to either unmute or put your video on, or just otherwise indicate a round of applause for Yaguang.
Thank you.
Thank you, Yaguang. Again, it's lovely to see everybody online, and I hope to see you all in person sometime in the near future.
Hi, everyone.
Everyone.
Nice to see everybody.
Thanks all. Been nice to see you all.